Hello and welcome to our final event for World Space Week. Today, we'll be talking all about alien worlds, that is, planets beyond Earth. I don't mean the 8 planets within our solar system that orbit around our star, the Sun. What I mean instead is those planets orbiting stars somewhere else in the galaxy. That's right, scientists have found planets that circle around many of those stars you see when you look up into the night sky. Isn't that amazing? Now, we have lots of schools joining us today, so welcome to all the classrooms watching and to those of you at home. You can let us know where you're watching from by typing in the Q&A box at the bottom of the screen, and we'd love to hear from you. To help us explore this fascinating subject today, I have Professor Carole Haswell with me, who is Head of Astronomy here at the Open University. And I'm Natalie, a science communicator here at the Open University. So my job is to help our scientists tell people all about the science that they do. We're based in Milton Keynes, where there are lots of scientists all working on different areas of science research. We also do lots of events like this one today, and there's more information on our YouTube channel, School of Physical Sciences, the Open University. Now, Carole's science focuses on those planets I already mentioned that orbit around other stars, and she'll be telling you a bit more about this very soon. Whilst you listen to Carole explain more, it's your chance to think of some questions you might want to ask her. If you're in a school and have a piece of paper, then write down your question to give to your teacher. You or your teacher, if you're at school, can start typing questions into the Q&A box at the bottom of the screen whenever you like, and I'll ask them to Carole very soon. Now, I think it's time we hear more from Carole, so let's welcome Professor Haswell.
Hello, thanks Natalie. Hello everybody.
So do you want to get started with your little presentation to give people a chance to think about exoplanets and all the stars out there in the galaxy and all the planets that might be around them?
Yeah, absolutely. Yeah, so as you can see on the slide, I'm an astronomer. And what astronomers do is to use telescopes. And I use telescope to collect starlight. And the picture you can see there on the left-hand side of the slide is a picture of me in front of a telescope, which is actually on a mountaintop in the Andes in Chile. And this particular telescope has actually found lots and lots of exoplanets. And I personally have been involved in projects that have found exoplanets using this particular telescope. So what we do is we point the telescope at a star, collect the starlight, and then we do some really intensive analysis of that starlight to look for signs of planets orbiting the stars. And I personally am particularly interested in rocky planets, planets that, like the Earth, we could actually stand on and walk around. May I have the next slide, please? So this work is tricky. And the main reason it's tricky is because stars are so much bigger and brighter than planets. So the picture on the slide here shows a tiny little segment of the sun, and then drawn to scale 5 of the planets in our own solar system. So you can see the Earth there and the other small rocky planets that orbit in the inner solar system. And then you can also see Jupiter, which is the largest planet in our own solar system, and that's a gas giant planet. So you would not be able to walk on Jupiter. Jupiter is a huge ball of gas, and so there's no solid surface for you to walk on. May I have the next slide, please? So an important thing to realize looking at this particular picture is that in order to be able to show the sun and these planets all in the same picture, what I've done is to squash up the distances between objects. So the sizes of the various objects are drawn to scale, but the distances between them are much, much bigger than shown here. Could we have the next slide, please? Okay, so to try and give you a feeling for the immense distances in astronomy, even within just our own solar system, if you imagine the size of a typical Year 6 child, it's probably about 1 meter. And the size of the Earth is 6 million times bigger than the size of that person. So the Earth is really very, very large compared to us. But when you start thinking about the distance to the sun, that's 150,000 million times bigger than a person. So the distance to the sun is 150,000 million meters. So that's really a very, very big number. And because astronomers work with things generally that are much, much further away than the sun, then obviously it's very, very inconvenient to be dealing in such huge numbers whenever we want to say the distance to something. So we use an alternative way of describing distances in astronomy. Now, the fastest thing that we know of, and actually the fastest thing that's allowed according to the laws of physics, is light. And light always travels at the same speed, the so-called speed of light. And it takes 8 minutes for the light from the sun to reach us here on Earth. So astronomers use that fact to establish a different yardstick for measuring these very large distances. And so the distance to the sun, an astronomer might say, is 8 light minutes. So if the sun were to tragically suddenly stop shining, we wouldn't know about that until 8 minutes after it happened, because light would still be on its way for 8 minutes after it turned out. So using the speed of light gives us a way that we can conveniently describe very large distances with numbers that we can think about easily, like the number 8. So can I have the next slide, please? So this is a picture of actually the same telescope that I showed you before, and the telescope that I was standing in front of is inside the larger of those two domes there. And this is a picture, a real picture that's been taken of that telescope at night inside its building on its mountaintop in the Andes. And in the night sky, what you can see is our inside out view of our own Milky Way Galaxy, which contains about 100 billion stars. And so this particular view is looking at the center of the galaxy, where there's really very, very dense stars. So you can see in this photograph, it just looks uniformly bright, but that light is the light of many, many stars, all traveling, sending their light waves to us so we can collect them with our telescopes here on Earth. May I have the next slide, please? Okay, so this is now to try and give you a feeling for just how far away the stars are. So as I just said, there are 100 billion stars within our Milky Way Galaxy. And what this slide is showing is a map of the very, very closest stars to the sun. So once again, the objects that are shown on this map are shown much bigger relative to the distances between them. So if you were to actually draw this to scale, the stars would be invisibly small points because they're so much smaller than the distances between them. So the very, very closest star to the sun is a star called Proxima Centauri. And that star, it takes the light 4 years to travel from Proxima Centauri to us here on Earth. So if you think about that unimaginably large distance from the Earth to the sun corresponded to 8 minutes, the distance between the sun and our very closest neighbor star is actually described by 4 years. So if you think about comparing 8 minutes to 4 years, that's a really big ratio. The distance to the nearest star is huge, and this is why we use these units, light years, to describe distances in astronomy. May I have the next slide, please? So planets are hard to find because they're small and dim compared to stars. And the nearest planet outside our own solar system that we found is actually orbiting that very, very nearest star, Proxima Centauri. So it took quite a lot of work using the telescope that I showed you the picture of to find that planet, but we did find it. And what we find is that whenever we look really carefully and analyze starlight, we usually find planets. And so the planets that we find orbiting other stars, we call exoplanets, to distinguish them from the familiar planets that we know orbiting our own sun in our own solar system. So we think that the 100 billion stars in the Milky Way Galaxy actually have more than one planet each on average. So there's more than 100 billion exoplanets in our galaxy. So that's a really mind-boggling fact. May I have the next slide, please? So far, we've actually been able to find definite detections of about 4,000 planets, generally around stars that are relatively close within the Milky Way Galaxy to the sun. But if we take, you know, what we find in the area around the sun and scale it up, assuming that there's nothing special about our own particular part of the galaxy, that's why we expect there to be more than 100 billion planets within our Milky Way Galaxy. So of these 4,000 planets that we found lots of surprises, lots of planets that we didn't expect compared to the ones in the solar system. Some planets have similarities to the planets in the solar system, but some of them are completely different to anything that we see orbiting the sun. And one of the things that astronomers are trying really hard to do now is to find Earth-like exoplanets. So that's one of the big things that we're aiming for now. So I'm going to stop there and give you time to think of some questions.
Thank you so much, Carole. This is such fascinating stuff. And I think for many people here today, like it might be the first time you've heard about exoplanets. I was speaking to my daughter, who's 5, about them yesterday, and she was fascinated that every star you see in the sky potentially has many planets around it, just like our solar system. And there might be worlds out there that are just like Earth. It's absolutely amazing. Now, one of the questions we've had in already was how many exoplanets are there? And luckily, Carole answered that during her talk. I just want to say hello to a few of you who've let us know where you're watching from. We've got some people in East Anglia and Northampton who are fairly close to Milton Keynes, but we've actually got someone in the Netherlands, so hello as well. We've got Churchgate School in Harlow and Hertfordshire School in Brighton. I'm actually from Worthing, just down the road from Brighton, so that's exciting to see you there. So we're going to give you a chance now to have a think about your questions and have a chance to actually put your questions into the Q&A box, because I realise with all the classrooms involved today, your teachers are going to be very busy collecting in your questions, and we want to give them time to not be completely stressed out on a Friday afternoon and be able to put your questions into the Q&A box for us. So if you want to hand in your questions shortly to your teacher, and if you're at home, start typing straight away. We can start looking at those questions soon. Now, you might want to know how you find exoplanets using telescopes. You might be wondering what these alien worlds that Carole's talking about even look like. What colour are they? What are they made from? And you might be wondering how long it takes to get to one of these in a spacecraft. Is that even possible? Whatever you want to ask, we're going to give you 3 minutes now to type in some questions into the Q&A box for me to ask Carole. Don't worry, if you need more time, you can keep typing throughout the event as Carole starts answering them. Now, we're going to be really helpful and give you a countdown clock on screen, just so you know how long you've got. So I'm going to say goodbye, and I will see you in 3 minutes. And hopefully I see lots more questions in the Q&A box for us to get going with Carole. Wow, okay, we have so many questions coming in, thank you. I fear that we may not be able to get through all of these today, but I'll let you know at the end how to contact us if you do want questions answered and we haven't been able to get through and got something that desperately needs to be answered. So I'm just going to get going, Carole, and you better be ready for this because we're going to get through as many as we can. Yes. I'm going to start with, you mentioned that you collected starlight. What did you mean by that?
So a telescope is almost like a big bucket, and you point it at the star that you want to study, and the light from the star falls into that bucket. At the bottom of the bucket, there's a mirror, and it's a curved mirror. So it's like if you go in a fun house, you don't get a true sort of reflection. And the curved mirror then focuses the light onto a detector, which will be very like the camera that you might have in your mobile phone. And so we collect the light on a detector, like the camera in the mobile phone, and then we read the information out into a computer and analyze it.
That's brilliant. So a really good question here is, what are stars made from? And an additional question to that, are they all the same?
Yeah, so that is a good question. So stars are mostly made of hydrogen. So they've got almost entirely hydrogen, but about 20% helium. And that's because hydrogen and helium were made in the Big Bang at the beginning of the universe. And then stars are actually factories which make all of the other chemical elements. And so all of the things that our bodies are created from, other than hydrogen and helium, were actually created in previous generations of stars. So each star is just formed from a collapsing gas cloud, and will have all of the chemicals that that gas cloud had in it will be collapsed down into the star. Did I answer both parts?
Yeah, I think so. That's brilliant. So our sun is also made of the same stuff. Have we got an unusual star? Or is it really similar to lots of stars that we see in the galaxy?
Yeah, so the sun is a fairly typical star. It's a little bit bigger and brighter than most stars, and it's also above average in the number of enhanced chemicals that it's got, sort of the elements like carbon and oxygen and nitrogen. So it's a little bit more enriched than you would expect for its age and location. But it's pretty typical. These are sort of nuances.
So what about the biggest star? Do we know what the biggest star is that we can see out there in the universe?
So it's quite difficult to be absolutely certain, because obviously stars are very distant, and to know how big something is, you need to be able to measure its size somehow. And we can't typically do that because stars are just so far away. All we see is a point of light. But there is a star called VY Canis Majoris, which is a huge star that's an evolved star. So when the sun runs out of hydrogen at its center, it then has to move on to the next stage of its life, and it becomes a giant. And so it will become very much bigger than it is now. And if you started off with a lot more material than the sun has, then you can be a supergiant star and be very, very much bigger than the sun is. And VY Canis Majoris, and its name just refers to the constellation it's in, Canis Majoris, and VY just says that it's a variable star. And it's a sort of a code name that astronomers can decode and know which star they're talking about. So that's the biggest star that we know of, I think, but there's definitely some uncertainty there. It almost certainly isn't the biggest star in the universe, but it's the biggest one that we've managed to get an indication of size for.
And is that one of the stars we can see in the night sky, or would we need a special telescope to see that?
I'm not personally sure how bright it is. So astronomers use a scale called the magnitude scale, and anything from 0th magnitude to 6th magnitude, if you go to a dark place and get dark adapted, you will be able to see with your eyes. But almost all of the stars are much fainter than 6th magnitude. So we only see the tip of the iceberg with our naked eye. And that's why astronomers use telescopes, because obviously a 3.6 meter light bucket is much bigger than the pupil of your eye. And it means that you can actually detect much fainter objects. And so that's why we use telescopes, to collect the light.
It just collects more light from that dark sky, because actually I've had the opportunity to go to some very remote places during my time, and when you get away from the cities and all the light of the cities and all that, what we call light pollution, and you get to out in the middle of nowhere, you can see so many more stars than you can when you're in a city. So it's actually, you know, it's something that's really fun to do. If you can do it safely and get out, you know, into the middle of nowhere and then just look at the stars, you'll be amazed, you know, what you can see then. It's quite fascinating, isn't it?
Mm.
Right, now I've got a really good question. I want to talk about stars first before we get on to the planets, because obviously this is the bit we can see, and then we'll talk about the bit that we have to kind of infer is there. Now, a good question is, how come Jupiter is a planet if it's made of gas? I know this is not really your research area, but I thought that was a great question because it's a really big planet, isn't it? And it sounds like it's kind of similar to a star.
Yes, well, Yeah, I suppose you could think of Jupiter as being a failed star. It just didn't have quite enough mass in order to be able to get hot enough at its center to do the nuclear fusion reactions that power the sun. So the sun is actually a factory turning hydrogen into helium, and that produces energy, which we see as the sunlight that heats the earth and makes everything possible. So Jupiter is classified as a planet because it doesn't do nuclear fusion. It's big enough that it's collapsed under its own gravity to form something that's perfectly round, or almost perfectly round. And it's also sort of the boss of its own orbit. There's nothing else at about the same distance from the sun as Jupiter to rival Jupiter in its size and gravitational influence. So it ticks all the boxes for the official definition of being a planet.
Brilliant. Okay, Jupiter's amazing, isn't it? It's right. I did have a great question here from Xavier, and he says, why did you pick astronomy instead of being a scientist? So I'll just point out that actually Carole is also a scientist. So we have lots of scientists that all work on different areas of science, and then what we do is actually describe them as something else as well as a scientist. So Carole is actually an astrophysicist. So this means she works on astronomy, looking at space and the stars and physics. So maybe I'll just rephrase Xavier's question a little bit and ask, why did you pick astronomy? What drove you to do this?
Well, I think when I was young, I was just very curious about how things work and why things are the way that they are. And I think most children are. And I think astronomy is just sort of a natural extension of that, just to sort of ask, why are the stars there? What makes them shine? Why is the universe here? It just seemed like a really interesting thing to do. And I suppose there was only really one other thing that I wanted to do, and that was to be an artist. And I thought that actually, if I studied maths and science, I was more likely to be able to get a job if I didn't manage to be an astronomer than I was if I tried to become an artist and didn't manage to support myself by making beautiful pictures. So there was a little bit of pragmatism and a little bit of inspiration, I think, in that choice.
Thank you. Now that's a great answer. Now I think I've asked quite a few star questions, so I'm going to start to slowly move on to actually the alien worlds, the exoplanets out there. And a great question is, where does the term exoplanet actually come from? Where does that phrase come from?
So exo, I think, is a Latin prefix, and it just sort of means outside. So the planets, from the point of view of science, are exactly like the planets in our own solar system. They tick all the boxes for the definition of a planet, except, I would argue rather short-sightedly, the definition of a planet specifies that the planet must orbit around the sun. So an exoplanet orbits around a different star, but it's, apart from that, exactly the same as the planets in our own solar system. And the exo is just put on the front to say this is a planet outside our own solar system.
Brilliant. I'm glad we've figured that one out. Okay, now I've got a great question here about how you actually find these exoplanets. And I think actually you had a slide prepared that showed some pictures of this. So would it be possible to get that slide up? And then maybe Carole could talk about this great question. How do we find them? Obviously, she's spoken about that we look through telescopes, but and collect light. But yeah, how do we actually see these things?
So there's two main ways, and I'm going to just focus on one of those ways because it's actually the method that's found the most of the 4,000 exoplanets, and it's also the easier method to understand. So in this artist's impression, the artist has shown one of the planetary systems that we found with the telescope that I showed you, orbiting one of the nearby stars to the sun. And there's a couple of rocky planets orbiting that star. And this particular image, the artist has imagined that he's sort of behind one of the planets, and you can see a closer orbiting planet which is just superimposed on the edge of the star there. So if you think about a planet orbiting a star, if it's lined up properly, once every orbit, it will get between you and the star. And so all of the planets in the galaxy are orbiting their stars at whatever angle they choose to happen to be orbiting at. But some of them, just by chance, will be lined up so that the planet actually crosses in front of the star from our point of view. And this is called a transit. The planet sort of transits across the star. And when that happens, as you can see in this artist's visualization, the planet, it's a solid object, it will block some of the light from the star. And so all you need to do to find a planet, if it's lined up in that way, is measure how bright the star is. And if you just keep measuring how bright the star is, if there's a transiting planet, you'll see a regular dip in the amount of light that you're managing to collect from that star, because the planet is blocking some of the light. And so this is a really easy way of detecting planets, because if you take something like your camera phone, but attach it to a really powerful telescope, you can actually measure the brightness of 100,000 stars all at the same time, and just keep measuring that over and over again. And some of them will show these regular dips when a planet gets in front of the starlight. So you can tell there's a planet. The time between successive dips tells you the length of the planet's year, and how deep the dip is tells you how big the planet is relative to the star, because the size of the planet determines how much of the starlight it blocks. So if you had a planet like Jupiter transiting across a star like the sun, it would cause a 1% dip in the amount of light that we see from the star. And that's quite easy to measure and has been done from the ground. And so we know lots of transiting Jupiter-like planets orbiting around other stars. For a planet like the Earth, which is about 10 times smaller in diameter than Jupiter, you only get a tiny dip, and you actually need to put a telescope in space outside the Earth's atmosphere in order to detect them. So this transit method has been the way that we've found about 3,000 of the 4,000 planets we know of.
There's so much interesting stuff to unpick here. And actually one thing I'll point out, just to remind everybody that yes, in our solar system, we have our star in the middle, our sun, and all the planets orbit around it in circles. And so that's partly what you were saying there. You can measure, and I should also point out, every time a planet goes around the sun once, that's a year. So this is how we can then look at stars and then their planets around them elsewhere. Every time it transits in front of that star, we know it's 1 year. Now, a year on Earth is different to a year on Mercury, for example, which is really close to the sun, or a year on Jupiter because it's further away. So years are very dependent on where you are in the solar system. Now, obviously, you've talked about that we found over 4,000 of these exoplanets, but there's probably hundreds of billions of them. Now, we have 8 planets in our solar system, and we have really nice names for them. And Sam is asking, what are the planets named after? So we know the ones in our solar system, but then we've got all potentially hundreds of billions more to name out in the galaxy. So how are we naming them?
Yes, so it would be nice if they all had lovely poetic names that meant something and described something about them. But in fact, because we're talking about so many objects, we have to be methodical, otherwise we just get hopelessly confused. So astronomers have a number of ways of describing particular stars, and most of them are really boring. So for example, there's a catalogue called the Henry Draper catalogue, and that has hundreds of thousands of stars in it, and they're all called something like HD, and then a long number that might be 856931. So that specifies the star. And if you find a planet orbiting around that star, the first planet that you find would be HD, whatever the number was, with a little lowercase b after it. And then if you find another planet orbiting around the same star, that would be HD, whatever the number is, C, little c, and so on. So our naming conventions are not very poetic, but they are sort of agreed so that any astronomer can know what the heck the other astronomer is talking about when they write about a particular planet. So it's not romantic, it's not satisfying, but it's precise.
And it's simply because there's so many of them, we would never be able to think of enough names, would we? We need a code, like registration plates of cars. You know, we have so many of them, we need to have a code and a system. So that completely makes sense, however boring it might sound. Right, now let's have a look at some of these questions again. One great question coming in, and I've been asked a few times, is how do we know what these planets are made of? Are they like Earth or are they like Jupiter? How do we find this out by looking at them through telescopes?
Okay, so in the solar system, there are two very distinct kind of planets. So there is the small rocky ones, Mercury, Venus, Mars, and Earth. And then there are the giant planets, Jupiter, Saturn, Uranus, and Neptune. And we do find planets of those two sizes orbiting other stars. And most of the time, we only know how big the planet is. And we assume that the little ones are probably rocky. And there's also more complicated good reasons for thinking that, because we have quite a good idea of how planets form. And the rocky ones basically form from a lot of little pebbles gradually sticking together under gravity. And they don't then collect a lot of gas, because they form close into the star where the gas can't exist. It gets blown away. But further out in a what's called a protoplanetary disk, so this is the gas cloud that the star forms out of, collapses down to form a star, and you get a disk of remnant material around the star, and that's what the planets form out of. The more distant parts of that disk will be very rich in gas and in ices, and that's where the giant planets form from. So if we see a large planet, we assume that that's a giant, and if we see a small planet, we assume it's rocky. And the giants have to be made of gas, because there just simply isn't enough of the enriched rocky material to be able to make such big planets. And we are able to, in special cases, measure something about the composition of planets, and that confirms the picture that we have from our sort of theoretical understanding of how planets form.
And a great question here from Callan, which kind of leads on from that. They ask, are there any ocean planets?
Yeah, so we think that there are. And one of the surprises when we started measuring exoplanets is that actually there's quite a lot of medium-sized planets. And those medium-sized planets are called super Earths or mini Neptunes. And there's sort of two possible types and maybe two schools of thought amongst exoplanet astronomers. So obviously a super Earth is a picture of a planet that's rocky like the Earth, but maybe 10 times as big as the Earth, or maybe not quite 10 times as big, 10 times as massive. And a mini Neptune would be like the giant planet Neptune, which is the smallest of the giant planets in our solar system, but smaller than Neptune, so a mini version of the giant planet. And the reason that there's this sort of tension between are they super Earths or are they mini Neptunes is that for a lot of these planets, basically what we've measured is how big they are. And we can imagine, and we can actually construct models using the laws of physics that we know to sort of theoretically build planets of that size with about 10 times the mass of the Earth, built from rocky material, or a more tenuous planet built from gas like the giant planets, but having the same total size. And one possible structure that you could have for a planet that fits that bill is to have a rocky planet with a huge amount of water. So the entire surface of the planet is covered in water and you have a very water-rich atmosphere. And it may well be that those kind of planets are quite common. And we have a lot of sort of question marks about planet structure and how planets are built. So these ocean worlds, I think most exoplanet astronomers would say, yes, they definitely exist, but how common they are is not clear yet, I think.
And I think it's good to point out at this stage that one of the reasons you seem to have a lot of questions and there's a lot of unanswered things about this area of science, and that's because it's relatively new, isn't it? We first discovered an exoplanet in 1995, which probably sounds like ages ago if you're in year 5 or 6, but believe me, it's not that long ago. And actually, that's a really new research field, isn't it? So like we've got so much to learn still about what is out there in the galaxy.
Yes. And this is a fantastic time to be an astronomer because we're just finding out new things on a daily basis. And I think the exoplanet area is particularly exciting because it's new for everybody. And so anybody can join in and not be very far behind the most eminent world-leading experts. So it's a really great area to.
Now, it's also really great because we get to talk about aliens, which is one of my favourite topics, and we've had loads of questions in about aliens. So it's the butterflies class, which is a year 6 class. I don't know where they are, but they've asked, have you seen some life on any planets?
Well, I think I have to say that personally, the only life I've seen is on Earth. And speaking for the whole of human science, I think I would say that no scientist would claim to have seen any definitive signs of life anywhere except for having an origin on Earth.
Oh, no, that's very sad. People are very sad, but do you think there could be life anywhere, even if we haven't seen it?
Yeah, personally, I think that there is almost certainly life elsewhere. And there are 2 reasons that I think that. The first reason is, as we examine the Earth more and more carefully, it turns out that there are microbes, single-celled life, in almost every imaginable niche that we can see on Earth. There are microbes living in rocks. There are microbes living in water that's very hot at the bottom of the ocean, where you've got vents coming up from the hot subsurface, where you've got conditions like a volcano. Microbes can live there. There were some microbes that were harvested, I think, from a cliff on the south coast of England and taken into space and exposed to the vacuum of space and returned to Earth, and they were still alive. So it seems to me that microbes can thrive pretty much in any environment where you're between sort of freezing point and boiling point. They seem to be really very robust. And the other reason that I think there's probably life in other places is if you look at the history of the Earth, there are signs of very primitive life dating back to very soon after the formation of the Earth. So from a sort of probability point of view, it seems like you don't need anything terribly special to form primitive single-celled life. So for those 2 reasons, I think that if we're able to make sensitive enough measurements, we very well may find life on some of the icy moons in our solar system, possibly on Mars. Possibly there's life in the clouds of Venus. There was a lot of excitement about a possible sign of life in the atmosphere of Venus a year or 2 ago. So I would be really surprised if there isn't life elsewhere. But I don't think we're going to find complex life like people and trees and dogs and horses. I think probably the life that's very widespread is probably basically slime. So that's either bitterly disappointing or quite fun. I don't know. Depends on your attitude to slime.
Very good. So Evan asks, what's the most Earth-like exoplanet? I guess we always think about Earth-like worlds because we know that has life and water on the surface. So have we found any of the exoplanets that we think are really like our own planet and that therefore might be able to host life?
So we've definitely found exoplanets that might be able to host life. So there are planets that are orbiting their star in what we sometimes call the Goldilocks zone. So they're not too hot, they're not too cold, they're at the right temperature to be able to have liquid water on their surface, like the ocean worlds we talked about earlier. There are quite often sort of stories on the internet about Earth-like exoplanet found, and I think whenever somebody finds a planet, you have a sort of, a parental feeling about your own discoveries and you want to make them sound as special as possible. So I think people tend to sort of emphasize the things about their own discovery that make them interesting. So if it's the same temperature as the Earth, or if it's the same size as the Earth, or if it orbits a star like the sun, you might emphasize that Earth-like property. But so far, I would say we haven't found any exoplanets that are like the Earth, an Earth-like planet with an Earth-like temperature orbiting a sun-like star. And there is a big mission which the European Space Agency is going to launch in, I think, 2027, which is going to try to find Earth-like planets orbiting sun-like stars using the transit method, which we talked about earlier.
Wow, I can't believe how quickly this session has gone. We did agree that we would try to finish at 2:45 because I know a lot of you are watching from school and it will soon be time to get home. Now we do have a lot of questions we haven't had time to get through. So we've got some ideas about how we might be able to answer that. It might be that we'll get Carole to record a little video answering some of these that we'll tag onto the end of this film when we put it onto our YouTube channel. We will let you know and hopefully we'll be able to update you. But if you do want to email us, then please do send an email, get your teacher to stem-communications@open.ac.uk. The link should be going into the chat box and we will try to get back to you. So many amazing questions though, and I'd really like to thank Carole for coming here today to talk to us all about her science. And it's so fascinating to learn about these worlds that are out there. There's so many of them. Now we've had other events this week as part of World Space Week. We had another one yesterday, also aimed at schools. So that's about icy moons. So we spoke about those a little bit today and about life in these icy moons. So you might want to check out that event. It will be available on YouTube later next week. You just need to search for the School of Physical Sciences, the Open University. Now, if the adults among us want to learn more about exoplanets to help maybe answer some of those questions from the children, then we have a free Open Learn course available, which we'll put the link for in the chat again. It was actually written by Carole and one of her colleagues, and it is suitable for anyone over 13, so not just the adults, so well worth checking out. And finally, we actually have a BBC documentary coming soon, which will feature alien worlds as part of the series. So do watch out for that later this year. And I'm afraid that is all we have time for. So thank you, Carole. Thanks for joining us. And we really hope you enjoyed learning all about the worlds beyond our solar system.